Normally, we don't think twice about taking a deep breath of fresh air. It's just automatic. But what actually dictates whether that breath is life-sustaining or literally toxic? Welcome to This Explainer. Today we're diving into a genuinely fascinating and honestly kind of terrifying natural phenomenon. We're looking at how the Earth's self-cleaning skies can unexpectedly turn into a lethal trap. And spoiler alert, it all comes down to a perfect storm of chemistry and meteorology.
So, on most normal days, the atmosphere is incredibly resilient. It's great at cleaning itself. You've got winds acting like giant brooms, just sweeping pollutants across the vast troposphere, and rain acting like a powerful shower, washing it all out. Plus, photochemical reactions break things down. But what happens when that self-cleaning capacity gets completely overwhelmed? Well, an invisible trap essentially slams shut, and the consequences can be absolutely devastating.
For a true atmospheric disaster to unfold, you actually need two distinct things working perfectly, or maybe I should say imperfectly, together. First, you need a chemical engine. That's a system generating new pollutants way faster than the atmosphere can possibly remove them. Second, you need a meteorological lid. Think of this as a weather-induced cap that stops vertical mixing from diluting all that toxic buildup. So it really takes both, a constant factory of pollution and a stubborn weather cap to create a full-blown catastrophe.
Okay, let's start with that chemical engine, specifically something called photochemical smog. Think of this like an interlocking puzzle. If you remove just one piece, the whole smog assembly line grinds to a halt. The three absolute essentials are volatile organic compounds, nitrogen oxides, and ultraviolet sunlight. These three get together and form nasty secondary pollutants like ground-level ozone. But the silver lining is, if you take away just one of these, like the sunlight and night, the whole toxic process simply stops.
Now, take VOCs for instance. Basically, these are chemicals with a high vapor pressure, which just means they evaporate super easily into the air around us. They come from things you'd expect, like vehicle exhaust, petroleum refineries, and everyday consumer solvents. But here's a wild fact. They aren't just man-made. Trees, things like oaks and pines naturally release VOCs like isoprene. In our chemical engine, these VOCs are the vital amplifier. Their reaction with atmospheric radicals creates this vicious cycle that lets dangerous ozone levels build up way beyond normal limits.
And we can actually watch this toxic cycle build throughout the day in two main phases. It starts with the morning rush hour. You've got all these high-temperature vehicle engines pumping NO and NO2 into the air. Then, as the sun gets higher in the sky, we hit the daytime buildup. That UV light breaks down the NO2, creating atomic oxygen that links up with normal oxygen to form ozone. And because of those VOCs we just mentioned, that ozone creation is massively amplified. It literally transforms an innocent morning commute into a severe afternoon health hazard.
So, photochemical smog isn't just the primary exhaust puffing straight out of a tailpipe. It's actually a toxic mixture of secondary pollutants cooked up by the sun. We're talking ground-level ozone and a really nasty eye irritant and plant toxin called PAN. And here's the kicker. Because this chemistry needs time and movement to react, the absolute worst smog often hits hours later and miles away from the actual traffic that created it. This perfectly explains why certain cities just get hammered by these conditions over and over again. It's definitely not random. The worst affected places share a very specific geographic and demographic checklist. Think of Los Angeles, right? A coastal basin ringed by mountains, packed with cars, and tons of reliable sunshine. Or Mexico City, sitting at a high altitude which naturally amplifies the UV radiation. Delhi and Beijing sit in semi-enclosed plains with low wind speeds. Basically, the topography and sunshine load the gun, and vehicle emissions pull the trigger.
But how exactly does this toxic mix get trapped right where we breathe? Let's quickly look at the baseline first, how the sky naturally cleanses itself. Under normal conditions, we have something called the environmental lapse rate. Sounds complicated, but it just means as you go higher up, the temperature drops. Since warm air naturally rises, the warmer surface air continuously floats up into the cooler air above it, carrying pollutants away. It works exactly like smoke going up a chimney.
Enter our second villain, the meteorological cap. A thermal inversion completely disrupts that natural chimney effect. During an inversion, a layer of warm air just sits right on top of cooler surface air. It totally flips the normal temperature gradient upside down. Because the cooler surface air is denser, it just can't rise through that warm layer above it. Vertical mixing is completely shut down. It acts like a giant invisible lid, trapping all that pollution right at ground level.
And this annoying lid can form in three common ways. You might get a radiation inversion on a clear, calm night when the ground cools down faster than the air about it. That's usually what causes your typical early morning smog. Or, much more stubbornly, you get a subsidence inversion. That's from a high-pressure system where descending air compresses and warms up, forming this persistent lid that can literally last for weeks. Finally, there's the valley inversion, where cold, dense air just drains down mountainsides and pools at the bottom of a basin. Whether it's a brief morning chill or a massive high-pressure system, these mechanisms completely shut down the atmosphere's ability to dilute pollution.
So what exactly happens when you combine an uninterrupted chemical engine with a stubborn, unbreakable lid? Now, it's really important to remember that a thermal inversion doesn't create the air pollution itself. It just concentrates what's already there. But when you have constant human emissions trapped by a persistent inversion, you get an atmospheric tragedy. Let's look at two of the most horrifying historical examples of when that cap held tight.
Let's step back in time to Donora, Pennsylvania. It's this narrow river valley town. On October 27, 1948, calm winds and a really persistent valley inversion settled over the area. Now, this was a mill town. They heavily depended on a zinc smelter and a steelworks that continuously pumped sulfur dioxide, zinc oxide fumes, and heavy particulates straight into the air. With that inversion acting as a lid, all those caustic emissions were trapped for 5 agonizing days. The air turned into a heavy, visibility-obscuring, genuinely toxic fog. It only ended when rain finally washed the inversion away on October 31st.
Within just 4 days, that toxic fog killed 20 people in Donora. The victims were mostly elderly residents who already had heart or respiratory conditions. But the true scale of this disaster was much, much wider. Half the town's population, we're talking roughly 7,000 people, fell seriously ill with chest tightness, nausea, and burning eyes. Even hundreds of livestock in the valley perished from the air.
Now, the contrast between Donora and our next example is pretty terrifying. While Donora's disaster in '48 was a very industrial nightmare, a valley inversion trapping heavy factory emissions, just 4 years later, London experienced a massive domestic catastrophe. London's event was driven by a completely different type of weather cap, a subsidence inversion from a high-pressure system. And the pollutants didn't come from a single factory. They came from millions of everyday home fireplaces and brand-new diesel buses.
In December 1952, a highly unusual cold anticyclone stalled right over London. The city was freezing, so to compensate, residents burned massive amounts of coal in their 1.5 million domestic hearths. With absolutely zero wind, a subsidence inversion trapped all that coal smoke, acidic gases, and diesel soot just a few hundred meters above the ground. The result? A blinding yellow-black pea super fog so thick it literally paralyzed all transportation in the city for days.
The human cost of this was just staggering. While the government initially claimed around 4,000 deaths, later epidemiological reconstructions revealed the horrifying truth. Approximately 12,000 excess deaths occurred from bronchitis, pneumonia, and cardiovascular failure. To this day, it remains the most lethal single air pollution episode ever recorded for a Western city.
But there is a bit of a silver lining here. These historical horrors catalyzed a massive turning point. The casualties in Donora forced the U.S. Public Health Service to finally establish a definitive causal link between emissions, weather, and death, which led directly to the U.S. Air Pollution Control Act of 1955. Similarly, massive public outrage over the London death toll forced the UK government to pass the Clean Air Act of 1956, mandating smokeless fuels and smoke control zones. Essentially, these disasters forced governments to create the foundational frameworks for the modern clean air regulations that protect us today.
Which leaves us with a really critical question to end this explainer on. We understand the chemistry of VOCs and NOx now. We totally understand the meteorology of thermal inversions. But as our global cities continue to rapidly expand with intense vehicle densities and complex new industrial outputs, that recipe for disaster is still sitting right there. So, as the weather changes outside your window today, just how safe is the air you are breathing right now?